Good morning to you all. I would like to know before I start my talk, all of you are high school children, am I correct?
Yes, sir.
That means 8th, 9th, 10th, correct? Okay, now I will talk about this field called cosmic rays. Okay, now what I will be doing, as Dr. Nagaraj said, was I will ask you occasionally some questions because should know how to proceed. And I hope one of you or some of you answer this. And so we'll proceed like that. It really does not matter if I don't go to the very end of the talk, because even if you understand the first few slides, it will be very nice. So what I'll be talking about is so-called cosmic rays. What does cosmic mean? Can anybody tell me? Cosmic. What does cosmic mean? Any idea? Yes, go ahead. Yes? Cosmos, okay, but what does cosmos mean? You're correct. Okay, I can't hear you, but essentially what we're saying is cosmic is not terrestrial, that means not something to do with Earth here. So, thank you, it comes from the cosmos, whatever cosmos means, and we'll see what cosmos means. And a very interesting thing about this subject is it deals with the smallest, that's the so-called micro, and the biggest, so-called macro aspect of the universe. How does it do it? It essentially is a study of lot of particles. Particles are the constituents of atoms, for example, protons, neutrons, and some other new particles which you may get introduced to today. And the macro is, where are they coming from? These particles. That is where we address things like galaxies and other things. So this is a field which deals with both the micro and the macro aspects of the universe. So how do I want to plan this? What I will do first is I will tell you how these were discovered. It's a very exciting thing, how these were discovered. And there are different types of cosmic rays. I'll tell you how, primary, secondary, etc., what they are. And as I said, we will get to come to know some new particles, which some of you may not have heard of. And then one of the very interesting things about this field is many important experiments were done in India. Okay, so there is a big connection between this field and India. And so there we'll talk about many experiments concerning particles called muons, neutrinos, gamma rays, etc. And the last part is what the field is today. And one of the exciting things about cosmic rays is they have got enormous energy. I will tell you how much, but later. So that is the most exciting thing about cosmic rays. And so we will see something about their energy, what type of composition means, what type of particles they are, where do they come from, origin, etc. So let me begin with at the very beginning. You see, long time ago, now it's long time ago, it's more than 100 years ago, actually the late 19th century, physics, people were doing experiments there, and something called radioactivity was discovered. What is radioactivity? If you keep some element there, what element? Let us take at that time things like, say, uranium. Uranium is one of the heaviest elements. And so what happens is, after some time, you see that it's giving out particles. So that's what we call radioactivity. And some of the very important physics came from that time, the radioactivity experiments. So particles which came out of these elements were alpha. Alpha is essentially a helium nucleus. Can somebody tell me about helium nucleus? How big it is compared to hydrogen? Hydrogen and helium, what would be the difference? Anybody? Hydrogen, tell me, what has hydrogen got? What's the great thing about hydrogen? Hydrogen is the lightest element. Correct? Yes or no? No, you got to say yes or no. Otherwise, say it. Okay. So which is the next heavier element? Helium, you know. So helium, actually the nucleus, I'll come to what nucleus means. Then another thing called beta, that's electron. Okay. We will see where electrons come into the atom. And gamma rays, which are photons, we'll see what photons are. Okay. So these were very important experiments. And so they were using so-called detectors. Detectors is something which, as the name implies, it detects the presence of the particle. It will find, like let us say there is some particle going through, it will detect it. It will find it and get it registered electronically or somewhere. Okay. So these were found with some detectors. And the very interesting thing at that time was the actual detector I will come to a little later. Okay. Let the moment just let us think of some instrument which, for example, finds particles. Okay. What used to happen was this radioactivity, as I told you, if you have an instrument, it will detect alpha rays and beta rays from the element. So take away the element somewhere. So still the detector is still sitting there. Should it do anything? Should it detect anything at all? Okay, it is meant to detect radioactivity. I have taken away the radioactivity now. Should it detect anything? No or yes? No. But the very interesting thing at that time was you take away your radioactive element, you still have your instrument, and still it's going on showing some particles. Detecting means showing somehow, okay? It will register electronically or otherwise. So people were very curious. This is around 1900, 120 years ago or something like that. And why are these detectors, they go on showing the presence of particles? So some people thought maybe it's coming from Earth, because slowly they were knowing about Earth little more than what earlier. They said maybe there is radioactivity. So it's catching radioactivity from Earth. If it is true, then what should happen? You have a detector and you have radioactivity coming from Earth and it is showing some particles. So if it is really true, then when I take it away, take it up, it should show less effect or no effect, isn't it? So what they did was, there is something called Eiffel Tower. Which city would that be? Great, thank you. So just around that time, about 20 years earlier, this big tower had been built in Paris. And so people said, let us take it to the top of the building. So what happened? No. Did your instrument show less and less particles? No, the particles actually increased. So it is a very big mystery. You have particles even at the top of Eiffel Tower. That's, I forget exactly how many, what the height of that. So you can also keep reading. I'm not going to read it, but some of you can read it if you want. So are these instruments picking up radioactivity in Earth? No. If it is true, we should go up and the effect should decrease. But the effect did not increase. So what do you do next? Fortunately, at that time, people knew how to go even higher than the top of Eiffel Tower. What mechanism, what type of vehicle would they have used? Can somebody tell me? You want to go up? Huh? Say it. Something I heard. Balloon. Okay. So, one person decided to go up in balloons, and let us see what happens. The next slide. This man is called, his name is Victor Hess. So he went, he took a balloon to height about 16,000 feet, etc. Those days they were all very daring men, you know, very adventurous. We just don't know what would happen, but still this man was very brave. So he took his, this is one of the detectors we call gold leaf electroscope there. Okay, and I'll tell you what exactly this little later. So you can see this graph here. This graph, as we went up, you see this is the number of counts, number of particles, let us say. Okay, and as he goes up, this is altitude 0, that means the base, and when he keeps going up, it's actually increasing. So what this gentleman did was, of course he did many flights actually, and so he said there is some particle coming from space, outer space, and they are triggering my detector. Okay, and later, much later, he gets the Nobel Prize. Okay, he made here for the discovery, and so these things were called cosmic rays. As I said at the very beginning, cosmic essentially means cosmos, means outer space. We don't know what exactly. We'll see later where exactly they come from. All we know is they just come from somewhere outside. So this is how 1910, around almost 100 years ago, this is what cosmic rays were found. Okay, but you want to know more, correct? So what do these particles do, etc., as we will see now. Okay. So cosmic rays were discovered in 1912. There's another balloon here. He showed that intensity of radiation increased, as I showed you in that graph. Somebody else also did another experiment. I didn't talk about it. So what are these particles which are coming from outer space? So for the next 20 years, there's a lot of discussion, a lot of experiments were done. Somebody said, no, they are photons. Photons with what? Einstein in 1905 said, light, you know, earlier people used to think of it as waves. Okay, waves means like your sound waves or something like that. And Einstein showed that actually you can think of light as photons, particles. Okay, so we use the word photon, very generic now. So people used to think maybe they're photons, light, just like in astronomy, you look at a star, the light comes from there. And so people thought maybe they're just photons. And that is why they called it rays, cosmic rays, you know, photon, light rays, etc. But some other people said, no, they are not photons. What is coming from outside? Particles. What particles? We will see a little later exactly more about these particles. We call it protons, etc. So finally it was found an actually charged particle. What is charge? Okay, now we have electron, a charged particle, a proton, a charged particle. What would be the difference? Anybody? Proton and electron, what would be the difference? Speak little louder. Stand up and say, because you will get prizes, as somebody said. Yeah, say it. Come. Okay, thank you very much. Hey, come on, give applause for her. Okay, so, no, tell me a little more about proton electron. She's very correct. One is charge, another is, positive, another negative. Any more differences? Little. They should also hear. Okay, now I'll come to that. Thank you very much. You have preempted me. Okay. So, okay.
Sir,
We'll do that
proton
later.
is heavier than electron, sir.
Say it again, sorry. Huh? Yes?
Sir, proton is heavier than electron, sir.
What did you say? Proton is heavier than electron. That's what she said actually. I don't know. She said it's in the nucleus, she said. Yeah, okay.
Both have equal charges, sir.
Proton is heavier than electron. By how much, I'll show you later. Yeah, if you want to, it's about 2,000 times. Okay. Very good. So they said it's actually protons or something else. And so some experiments went on. But we want to know more. Okay? So let's go to the next slide. And what is actually happening? You see, I'm giving you a picture which we know today. At that time in 30s, they did not know that. But what is really happening is some particles come from somewhere. As I said, we don't know where. Once they come, and what do we have in atmosphere? We have something in atmosphere. You have your gas. So you have some nucleus sitting there. So it interacts. Means it really hits actually. Whenever two particles hit each other or whatever, you get other particles out. We'll later see what those are. Don't worry. So these particles, as we'll see in the next 1 or 2 slides, they go on interacting with, they produce more and more particles. Okay, that's what it is. And so slowly it comes to our ground here. So if you're sitting somewhere here, this is at the mountain, doesn't matter, maybe this is Bangalore somewhere. So you will, if you have detector sitting, it will record lots and lots of particles. Okay. So which height it is, as this shows, it is somewhere here. This is in grams per centimeter square, and this is in atmospheric. This is actually in kilometers, I think. Feet. Okay. Next. This is described little more in the next one. So first, actually, what happens is one particle comes, it hits some nucleus. So something called pions. We'll see what pions are later. Don't worry. Okay. And actually, it's much more complicated. There are many more particles coming out. And this is actually what happens in the atmosphere. Okay. Primary is called primary. These are called secondary cosmic rays. Actually, here also I showed one interaction. This is actually from one of the later accelerator. What is an accelerator? Essentially, we'll again talk about it, but something which produces a lot of very high energy particles. And they can actually look at it in the lab. They have what you call control. They see exactly what is happening. So plenty of particles come out. Probably 1,000 depending on the energy and all that. So we have 2 types of cosmic rays now. We have primary, which is this guy here, coming from somewhere outer space, we don't know. We'll see. Its energy is very interesting. And once it starts interacting, we have all types of secondary particles. So mostly when we're doing experiments here, we deal with secondary particles, secondary cosmic radiation. Okay, this is much more. Okay, now we will see here. Okay, so this is again, what happens, this is actually in the laboratory. What this is here is, as I'll show you later, something called a cloud chamber, which goes on, which shows particles, trails of particles. And here is a lot of lead. Lead is, so okay, what is the difference between lead and hydrogen? Lead, what could be the major difference? Lead, come on, you know. Huh? Yes, metal. But is any other difference? Let us say lead. You know, you are familiar with periodic table to some extent, correct? Huh? Much heavier than hydrogen, correct, yes. We actually, why we need heavy elements, we'll talk about later if you want. But, so these are all lead plates here. So what happens is, they'll start producing, just like you saw it, but this is actually, you're seeing it really. All this is just, I mean, we're imagination, okay? What happens, this is in the atmosphere, but I'm showing you really, if you put detector, whatever it's called, cloud chamber or whatever, so you can see how it grows, and again how it actually comes down, okay? The number comes down, we'll see that. So this is just same thing which happens in the air, keeps happening. Now lots of cosmic ray particles are going through this room, secondary cosmic ray particles. And like last Dr. Danal explained, she was saying about the neutrinos in the room. We'll talk about neutrinos much later, but so this is the particles here, for example, and so this has got all types of things happening here. Let's not worry. So this is not just one. Lots of primary particles come, all directions, all over the space. And this is shown here, and they make cascades. And so if you put some instrument here, they'll just keep on. Have you brought your beyond calorimeter, Nagraj? It is there. Viewers can be seen? Okay. So if we go up, you can see particles there, beyonds. We will come to beyonds later. Okay. So this is the story. Now, okay, now let us get familiar with the energies he brought. Okay. So usually you know what args and you know joules, things like that. Now in this field and in nuclear physics also, we use the so-called electron volt. What's an electron volt? Electron volt is just energy gained when an electron is put through a potential difference of 1 volt. Simple. And it has some number, 10 to the power minus 19 joules or something like that. So here, why we use these electron volt, you can see very clearly. Now, I think, did we discuss, for example, I told you Einstein said light can be in waves and particles. So, just this light here, optical light, what type of energy it has? It has very simple, very easy to remember, just 1 volt, something like that. It will be different, 1 electron volt. Okay? So, in that scale, you know, you go take X-rays, correct, in medicine, in hospitals. So they're also photons. What type of energy will they have? 1000 electron volt, okay, already very high. Now something called gamma ray. These are all different names. Essentially, we are increasing the energy of photon more and more. So these are gamma ray. So Einstein also told us that mass and energy can be used essentially interchangeably here. Okay, so E equals mc squared is something which you probably know. And so using that, we now what we do is we talk about mass in terms of electron volt. So 500 million electron volt is what electron has. How much is a billion? How many zeros? Somebody, how many zeros in 1000? No, somebody, one person get up and say, come on, come on. From this side, nobody is answering. Come on, boys, please. How many zeros in 1000? Simple. 3. How many zeros in a billion? Billion. You are 9 correct, but something else. Billion is how many? 3, 6, 9 goes like that scale. Okay. So your GeV is actually billion. Somebody called it G for some reasons. So if you go for a proton, actually it is 1000 GeV, about 930, but don't worry about that. So that is the type of energies. You should get familiar with this because nuclear physics and this field I'm talking about, we all talk in terms of energy, electron volts. Okay. Now let us see more. What do this mean actually? Okay. There is some definition of Joule which you probably all know. Okay. So now let us increase the energy of a proton somehow, and we go for actually 10 to the power of 19 here. 19 is a very big number. So what type of energy has it got? So all you do is multiply that by your, what is the 1 electron volt 10 to the power minus 19. So it will have 1 joule energy. Now in ordinary parlance, joule is not big. But please understand, 1 particle will carry that much energy. That's huge. Huge spelled with a big H. Okay? So it is like tennis ball thrown at very, very high speed. But as I say, it is actually a proton which has got that. And so we are talking of that much energy in cosmic rays. Compared to this, accelerators I told you are essentially machines which give energy to particles. Okay? And they started around 1930s. And we have the biggest today called the LHC, which I'm sure you know because of newspaper reports. And the energy today is TeV. What is TeV? 1000 GeV. So it's still very less compared to cosmic rays. So this is what I want to hammer, that cosmic rays have much, much higher energy compared to even what man has been able to do. Okay. Next. Okay, this is something called energy spectrum. Now, I hope you are familiar with graphs. Graph here, what we do is essentially plot y versus whatever is y versus x here. Y is the number of primary cosmic ray particles. I'll talk about this here, but later go to that. You see, this is the number of cosmic ray particles, and this is the energy. I don't know, can you see this number? Backbenchers? Hello, yes or no? No, can you read out? 10 to the power of 20. 10 to the power of 20 is enormous because 1 billion is 10 to the power of 9. Okay, 1 trillion is 10 to the power of 12. So we have particles of all energies here. And so here is how it really changes with energy. And this is what we call an energy spectrum. Okay, and it also shows as you go higher in energy, actually you will get less and less primary particles. Okay, so here it's again shown, as I was telling you, the LHC, which discovered Higgs boson several years ago. That's the energy it has. This doesn't matter at the moment. Okay, this is the highest here. Okay, now, what do these cosmic rays have? As I said, mostly protons. Let's not worry at this moment, and I'll skip this part. And okay, well, as we saw in those photographs, what really happens is particle number increases, stays put for some time, then number decreases. That is what we call a cascade. Cascade is just something which just a lot of things there. And here is again another graph for you. I'm sorry, there are lots of graphs, but let's understand just what happens here. I told you, number of particles go on increasing. So this is the number of particles at different depths in atmosphere. Okay, so you see, you can see first interaction takes place, number increases, then they start dying. Okay, because they don't have any more energy to do anything. So this goes. These are called cascade curves. So the highest which we have here is something here. So it has got more particles. This has got less particles. So now what we are, as I said several times, we will be somewhere here. So we will catch all this number of particles. Let us say somewhere here or here, depending on mountain or sea level. Okay, now I've been saying detector, you must have been tired about the hearing. What exactly is a detector? We said it detects particles. It's a very simple, again, it's the same thing. But how is a particle detected? Now there is something called ionization. What is ionization? Anybody guess? There are numbers there, no? They're written ionization. This is English. Okay, anybody? Okay, what happens is you have an atom, which I think I'll show you somewhere here. I had that slide, I think it is. Okay, now you have an atom here. I'll come back to this later for some other purpose. Okay, now it has got nucleus here. This is a carbon atom, 6 protons, 6 neutrons, there are 6 electrons. Why this should be same? I don't know, you can tell me later. Okay, so these are electrons here. So this is a stable atom, nothing happening. 6 here, 6 there, like that. But something happens when another particle comes, it takes away this electron, okay? And that's what we call ionization. And that electron will go and get detected because it's a charged particle. Charged particle will get detected here, is the detector, as I'll show you, because it has charge, whereas a neutral particle, which we will talk about a little later, won't have that. So these are several instruments. I'm sure you have not seen any of them. I don't know whether Visvesvaraya Museum has a GM counter, Geiger counter. No? Okay. So you should get one Geiger counter. Huh? Oh, electroscope is there. Great. Okay. Okay. So please, you should try out this electroscope. It's a very ancient instrument, but it's still very much used today. Okay. So here we have several. We have GM counter, which is actually very easy to build. What GM counter does is essentially detects particles, and as I said, charged particles, and it will have, I don't want to go into this one. You can ask me later if you are interested. Another thing called cloud chamber, which will show you the GM counter gives you an electronic signal. But this one shows actually. Already I showed you, for example, here. This is what is a cloud chamber does. It shows all these particles here. Okay, I gave it for some other reason I showed you, but this is a cloud chamber picture. Okay, so we have several like that. So there are many different detectors I won't go into. So the most which are being used were GM counter and at that time cloud chambers and electroscopes. Okay. Already 30 minutes over. Okay. So, okay. Now, let us familiarize ourselves with the classical particles. Okay. Now, we have talked about atom. Here is your atom. Here is your atom. There is something called nucleus. There are electrons here. Okay. Till about 1930s, we knew only 3 particles. Actually, Neutron was discovered somewhere around 22, but anyway. So we came to know about neutron. Okay, the very first particle to be discovered, can anybody idea? Very first particle to be discovered. It's a very familiar word is there. Huh? Yes? Exactly, electron. Actually, 1897 it was discovered. Okay, and so later proton in an experiment by Rutherford. Have you anybody heard of Rutherford's experiment? Yes. Oh, come on, say a little. Come on, you behind you.
He's giving the right answer, but he's not able to hear. So you say it loud.
You see, there are 2 things. You are speaking very low, and my hearing also is less. So
you stand there, you hear low. So please give your right answer in a loud voice so he can listen.
okay. Now, actually, somebody.
Excuse me, sir.
Yeah, Rutherford. Sorry, these people have said first. Okay, I'll come to you later. Okay, say it.
Sir, Rutherford, his experiment was about gold foil.
Yeah?
He passed some alpha particles, very electric, positively charged particles toward a gold foil.
Yes.
Many particles went through the gold foil, but many were deflected at uh, very large angles. Thank you, sir.
Yes, and then go ahead. Yes, correct. Very correct. Then, how did he explain that? You are very correct. Rutherford's experiment is exactly what you said. Okay. Now you tell me later. No, not now. Somebody else? What did he gain from that? He did an experiment. You see, wonderful experiment is done. But you should learn something from the experiments. Correct? So tell me, and you, come on. Somewhere, no, you can give this thing note to them. One mic can just float around. Mic can float around. Okay? Yes? We have all the time. It doesn't matter if you don't finish. I won't finish anyway. So, yes, good.
Nucleus was there inside the atom. That's why many particles were written back.
Yeah, why did they go back? For example, some of them went back.
Nucleus, in the nucleus, protons were there. When the particle hit the proton, it returned back. That's why.
Okay, particles hit the nucleus. Okay, at that time we didn't know about protons. You are very correct. Something heavy is sitting there, and something light comes and hits. Okay, so what happens? It's gold nucleus. Here is alpha particle, helium nucleus. So, as you said, something came back, and he said, okay, there is something very heavy sitting there. Okay, and Rutherford came up with his atom model, which is very simple. He thought of solar system. Okay, solar system, you have the sun, heavy thing, and you have the electrons, planets going round. So Rutherford said, why not? Atom also is like that. So he said something heavy, he called it the nucleus. Later they found their protons, that later, okay, and electrons are going round. So this is what your thing says here, okay. Actually, but at that time, of course, we didn't know neutrons. I'll come to neutrons a little later. So this is your carbon atom. Helium, of course, has just one proton and one electron. Okay, so here is some detail: neutron, proton, electron. So what's the difference between neutron and proton? Let us find out. Any of you? I'm glad you are answering. Now you can answer. Yes, you are not. Yeah. Take the mic. So I'm asking her, what's the difference between proton and neutron?
Protons have a positive charge, whereas neutrons are just neutral. They don't have any charges.
Neutrons have no charge. Okay. So is
They're
neutron are the same mass, whatever you call? Do you know how, in terms of weight? Okay, it doesn't matter. We don't want to go about the differences here. Okay. So about 1000 GeV, all of them, 1000 MeV. Okay. So now, but there are questions here. You please read that. Not just the graphs there, not just the figures. You have questions here. Now, at that time, these questions were being asked. We talk of a particle. What's a particle? Already proton. Now, the questions were raised, people raised, some very brilliant people. Are there antiparticles? What could be antiparticle? You just think of this. I wish I had hydrogen, it would have been easier. But you just think of something called antiproton. Just put anti in front of proton. Okay. But what could be the difference? 10 more minutes. Oh. Okay, I will finish it here. I have not yet come to. Okay, it's good. Okay. So essentially what would be an antiparticle for a proton? What's the main thing you think of in a proton? As you said, positive charge. So now antiparticle will have a negative charge. So antiparticle and particle. Okay. So same thing, anti-electron. So are they there? Some great theorists said maybe they are there. Then another important thing is, how do you bind these protons and neutrons? Why? What's this question of bind? Because, as you know, in electrostatics, you bring in the same type of charges, they repel. So you have protons sitting there, 6 protons here, for example. How do they sit there? Okay, So there is something else attracting. Okay. So these questions were being asked in the 1930s. How do you bind protons? Neutrons, there is no problem because they don't, but they also have, but that's a different story because they are uncharged. Okay. So now I will just end with the next 1 or 2 slides. The answer to this we got from cosmic rays. Okay. So at that time, some of the answers we got for these things. One gentleman really discovered the anti-electron. Actually, it was given a name called positron. Okay, and I don't know how many can see. Actually, this is the cloud chamber I told you about. For example, the particle positron goes this way. If it is electron, it would go the other way because there's a magnetic field. So what is the positron and electron? Positron will have positive charge because electron is a negative. So these are antiparticles. Everything else they are same mass, same speed, etc., etc. But it's only in charge. And another question we asked was what binds them? What binds them is what we call nuclear force because they are sitting inside nucleus. Another force we know is electrostatic and Coulomb force. And so what people are saying, if there is a force, there has to be a particle associated with that. Just like electromagnetic force, I'm sorry I can't talk much about, there's photon. So we have something called pi meson, okay, and that was what was discovered in cosmic rays. This is something called emulsion, like just photography. You just put photo paper sheet and somehow you get it, that's what it is. So I end here. Then what happens is accelerators came, much better things they could do, better, bigger, because they could study very detailed. So that's what we call really today experimental high energy physics. But, and I'll end this with that, there's still a lot of unknown things are there. And another thing, as I kept on saying, cosmic ray energies are very huge. So still accelerators have not reached it. So cosmic rays, there's still a lot of being done. I'm sorry I don't have the time to do any more. Thank you very much. What do you want me to do? I've been asking questions throughout.
So you can ask some questions if you want.
Yeah, you should ask me now.
Come on, you should feel.
And I mean, did you understand all that? Maybe some of you guys understood. But overall, I'm asking. Do you have any doubts at all? No, if it was a school, I would not, because I don't have time. If it was a school, I would just stand here. I'll make you people ask questions. Okay. But unfortunately, Dr. Godbole is waiting. She wants to give the next lecture. So we don't have much time. So, yes. Any questions? Okay. Good. Okay.
Who discovered cosmic rays, sir?
I need.
Who discovered cosmic rays?
Okay. Who discovered cosmic rays? It's not very. Okay. Anyway, thank you for the question. How were they discovered? I want to ask you. We'll come to his name later. His name was there. How did they discover? But that's my question to you. How did they discover cosmic rays? Yes, please.
So,
Okay, later.
Victor Hess in 1912 said that the particles coming from the sky, we don't know what is it actually, some particles coming from the sky. He wanted to know more about it, so he discovered cosmic rays. He said that there are some particles coming from the sky which is coming to the land down below,
Yes,
and they form a lot of particles. So to know about that, he got into cosmic rays.
Yeah, yes, you're half the story. The thing is they wanted to know whether they come from ground or they come from space, cosmos. Okay. So he took it up. Mr. Hess, his name, from Austria. So he took it up in Bangalore. Yeah.
And he thought that if some people thought if you take up, it will decrease. But what happened when he took it up, it increased more, sir.
Very good. Thank you very much. Okay. Thank you. She completely explained what I took for half an hour. Very good. Okay. So let me ask you about a little more, one or two questions. What about nucleus now? Okay, you have. Cloud chamber is what happens uh, when a particle, charged particle passes through. Okay, just like you have what we call compressed gas there. Okay, and then there is water vapor, and when a particle goes through, it acts like a nucleus. Okay, they form on the top of that, and so when you put light at that, somehow you'll see the picture as I showed you. So that is the cloud chamber, and today it is out of those days it was there. Today nobody uses that. Thank you. This side. Oh. Any more? Anything about nucleus? Little, though it's not doesn't. I didn't come to neutrino at all.
Excuse me, sir. Sir, are cosmic ray harmful to us, sir? Are they harmful to us, to human beings?
This question, actually, I even had a slide. No, they're not. Otherwise, you see, they have been there till the beginning of whenever Earth was made, which was some billion years ago. Okay. And so they have been around. And for example, we talked about neutrinos earlier. Many pass through you. Nothing happens. Okay, of course, they don't interact. And cosmic rays, of course, are charged particles. Some of them they could interact, but it really does not harm you. Hey, I have it. I have one slide actually for you. You see, it shows, it's a pie diagram, and it shows what type of radiation we experience. Most of these are actually from rocks, radon gas, etc. Half of it, actually, we get exposed that way. So only 10% of the radiation human body experiences come from cosmic rays. And so it is true. I mean, the point is just like that, it does not matter. It doesn't harm. But some of the so-called mutations during evolution could have been due to cosmic rays. Okay. But that is, we don't really.
Sir, and what are they useful, sir? They are useful, sir?
Now, you see, useful.
In what way, sir?
Okay. Now, what do you I think this I think we should talk. You see, what is useful now? Let us ask. Now, you see, the point is this. We are looking at some property of nature, what happens in nature. Okay. That is basically we are curious about things. Okay. So that is our main aim. So what did all these people do? They try to look for these particles, they try to find what they are, etc., etc., etc. As such, nobody thought of any use as such, because this is called fundamental research, fundamental science, so the knowledge increases. But there is another thing. Because we also learn a lot about these things, we build new instruments. Okay? So these instruments will be used somewhere later. And one of the greatest uses is here itself I put medical uses. Okay. Now actually the so-called pions and other particles I was talking about, positrons, they are used today in hospitals. Okay.
Yes, sir.
Now just like that we would not have known about positrons. Positron is some guy, one guy called Anderson, who just did an experiment, who detected it. And even got a Nobel Prize. But at that time, nobody knew what the use of positron is. But today, it's called positron tomography. Okay, so it can be used in hospitals, just like your X-ray, but much more precise because of certain reasons. So hadron, we call it, it's a different a group of particles, okay, pions and other things. So hadron tomography is there. So that's the use. But as I keep saying, when it does these things, not because of what use it might have, because we are curious. Okay? Thank you.